In this example, we're going to look at using a linear regression to estimate the value between data points that we've collected. Now, for all of these regressions, we don't necessarily know beforehand what type of regression is going to be good unless we kind of know something about the process that's creating the data. But we can get an idea once we plot the data that we've collected of what type of regression might explain the ordering of the points that we have. So in this example, we're given just data. We've collected after 1 minute, 2 minutes, up until 10 minutes, the amount of precipitate that we have from a reaction in grams. And we want to be able to predict or estimate how much of the precipitate must there have been between the data points that we measured. Now, one way we could find that is if when we ran this experiment, we sampled or took data more often than every 1 minute, so every 30 seconds, or every 10 seconds, or every 1 second. But in this case, we already ran the experiment and we don't have the actual data between 1 and 2 minutes, 2 and 3 minutes. So what we're going to do is make a regression so we can at least get an estimate as to how much precipitate there must have been. Now the regression is more or less kind of a guess. We don't actually know how much precipitate there was, but we're going to make kind of the best estimate we can based on the trend of, in this case, the weight of the precipitate over time. So the first thing we want to do is enter the actual data that we were given. So again, we have the time stamps of when we took this data, 1, 2, 3, 4, etc. minutes. Get rid of this. So we have our timestamps here, 10 seconds, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. And our weight, I'll have W. So we have to type this in because we were not given, in this case, a CSV file. I'm making sure all of our data is typed in correctly. All right, so there we have our raw data, we have our timestamps and the weights at those times that we measured on our scale. All right, so first we want to see how do these line up. So I want to plot the weight versus time. And actually, because this is collected data, or what we call empirical data, I don't want to put that line between them because I don't know how they're connected yet. So I want to put just the data points themselves. So I'm going to just make black circles to represent the data we actually collected. I'm not yet going to assume how they were connected. Put a grid on, and let me label this. So in this case, my x-axis is time, and we were measuring this in minutes. And this is going to be how much of the precipitate we have. And that was being measured in mass, really, in grams. All right, so in this case, we look at the actual data that we collected, starting at 1 minute, going to 10 minutes. And we see kind of this upward trend of the mass of the precipitate over time. So we have an infinite number of choices of regression or kind of filling in the gaps in time. So if our question was how much precipitate do we have at 2.5 minutes, right now we can't answer that because we didn't collect data at 2.5 minutes. We did collect at 2, we did collect at 3, but not at 2.5. So what the regression is going to do is kind of fill in the gaps of data that we're missing. So what we want to start with is what's the trend we have in the data? What's the relationship between the mass and the time for this example? And that's where we're going to start to make our assessment for the regression. So we see here it kind of looks like it's a linear trend in the amount of precipitate we have versus time. So they increase at a steady rate. So linear means that that slope would be constant from 1 minute to 10 minutes. And we can try many different fits and visually see how they line up, and also look at the goodness of fit and other types of parameters that come out from using the fit. So I'm going to start by making my fit type. Now I can go back and change this if I want. So I'm going to start by assuming it's linear, meaning that it's going to have some offset and some slope. So a linear is in the form, if you remember back to to geometry or to algebra, it's in the form of mx plus b, and that's how I'll write it for right now. So for fit type, and actually there's different ways I can express this. I can say it's m times x plus b. And fit type by default is going to assume that x is our independent variable. In this case, time will be our independent variable. So we're going to find a slope m and an intercept b for a line that best goes through the data that we collected from this experiment. All right, so I have my fit type, and if I check that, it's in the form mx plus b. And now what I want to do is actually run my fit. Right, so I'm going to use this fit command. I have to take my independent variables, which is my time, my dependent variables, which is the weight, or really mass in this case, and then the fit type that I want to use. In this case, I saved my fit type in the variable ft. And I can run this fit. Right, so one thing about using fit, we see that through an error here, the x must be a matrix of 1 or 2 columns. That's being time. We see here the way I defined time was a row vector. Fit is very picky of how you give it the data. It wants column vectors for the independent variable and a column vector for the dependent variable. So we see now this W transpose is now a column. So now if I run my fit, it's going to do it properly. Don't worry for now that we're not providing a start point. We're going to address this later. There's different types of fit options. Right now it will still give us a good result. Right? And we want to save our outputs from the fit. I'm going to call my fit function f here. I want to save my goodness of fit. I'll call it gof. And I'll save the output. So three outputs we have from using this fit command. Now, if I run this, I look at the results since I didn't suppress it. I have my model. I found the best M and the best B that fits this data. If I look at the goodness of fit, all we're going to look at for right now to kind of assess how good our fit is this R-square value. In this case, we have 0.9971 or 99.7% R-squared, which would be usually we would consider that an excellent fit, that this line fits our data very, very well. And then in our output, we're not going to be too interested in this right now. So let me clear this. All right, so we rerun this. We have our raw data points here. We saw that this line did give us a very good goodness of fit, or a very good R-squared value. But now what we can do is plot our fit on top of the original data, so we can also get kind of a visual inspection of how good this fit was. So I'm going to make a new variable t2. Again, this is going to fill in the gaps from the actual data that we collected. So I want to go from my smallest time to my largest time. So I'll just use min of t and max of t. And now I didn't have 1,000 data points in there before, but with the regression, I'm able to fill in all of those pieces. And then what I'll call W2, which is going to be the estimates, or the regression values I get for these weights or for these masses, I'm going to use this function f and evaluate it at t2, which I have to define first. So what this is doing is it's making all of these estimates as to the weights at all of these intermediate time steps, all these values that t2 has that we didn't have from our original data. And now in my plot, let me add on to my plot. I'm going to add a hold on to it because I want to, on top of my original data, which are those black circles, I'm going to plot my estimates from the regression as a red dashed line. All right, so now we can see visually those black circles, the original actual data points that we have, and now this red dashed line is from the linear regression, our estimate as to how much precipitate there was at all times between 1 minute and 10 minutes. And now we can also go back and answer maybe one question that we had, an estimate as how much precipitate was there at 2.5 minutes. Again, we know at 2 minutes there was 9.43 grams because we measured it. At 3 minutes, we measured 15.54 grams. what we can do here is assess using this regression function, or the regression that we found, big F. I can evaluate this now at specifically 2.5 minutes. So our estimate to how much precipitate there was, 12.3 grams at 2.5 minutes. Okay. And to clean this up a little bit, I want to make sure that I include in my legend what all of these things mean. So in the order I plotted it will be my empirical data. And then the red dashed line is my linear regression. And we see that it put the legend on. But I actually don't, it's covering up some of my data. I can move the legend using the location command. So after I label, in this case I only plotted two things, empirical data and linear regression, so I can actually add a third argument for the location. And here I can pick northwest, northeast, southwest, and southeast. And then there's other options too, and that's going to be where does it put the legend. So by default it chose to put it in the northeast corner, but it would be better in the northwest corner because it won't cover up data that way. So if I rerun just this legend, then we can see the plot. We can see now that it moved the legend to the upper left or the northwest corner, and it's not covering up the data as it was before. Right, so again, in summary, I plotted my original data, those black points here. Let me go in order again of what we did. The original data, it looked more or less like a linear relationship between the two, so a constant slope of the mass of the precipitate increasing. So I tried, in this case, the linear fit type of mx plus b. Actually, as an alternate, it also works if I put poly 1. So that's polynomial first degree. A first degree polynomial is just a linear relationship. So let me comment that out. I'll rerun this and we'll get the exact same results. All right, so I do a poly 1 and I do my fit command. And again, in my assessment, I can check that goodness of fit as one way to see how, as the name implies, good the fit was. Specifically looking at the r squared, we saw it's very close to 1, which is the highest it could be, which would be a perfect regression. And then visually, I can plot on top of my original data, I can plot my regression line, this red dashed line, and we see that lines up very well with the actual data that we have. And this was all saved into this function big F for our regression. And again, we can use this to assess what the mass of the precipitate was at any point between 1 and 10. So here, if we wanted to know our estimate as to how much precipitate there was at 3.6 minutes, it says 17.03 grams. What fit also lets us do, although it's dangerous to do this, is not only can we what's called interpolate, or find data between points we actually measured, but it lets us extrapolate as well, which means that we go outside of data that we measured to make a prediction or an estimate as to how much, in this case, precipitate there would be. So we only actually measured to 10 minutes, but because we have this relationship, if we assume, which could be dangerous, but assume that that relationship after 10 minutes continues in that same way, we can make an estimate that at 11 minutes we would have 48.8 grams of precipitate. Now we can be more certain that what's happening between data points we measured is a pretty good estimate, but something could happen with our reaction after 10 minutes that we didn't have a chance to measure because we ended the experiment there. So making the assumption that the relationship holds up outside of the data that we collected can again often lead to erroneous results or wrong results and bad predictions.